In this video, we are going to talk about Fourier series and some intuitions therein. Consider that we have a periodic signal x of t, and this signal is periodic with respect to time period t naught. So x of t plus t naught or t minus t naught is giving back our original signal, which is x of t, and hence it's periodic. So this signal is periodic for all values of t. So this is our time period of the periodic signal, and also from here we have f naught, which is equal to 1 over t naught, and this is our fundamental frequency. So we have a fundamental period and fundamental frequency that we can extract out from this signal. Also the fundamental angular frequency, that is omega naught. So this is equal to 2 pi f naught, or simply 2 pi by t naught. So this is our fundamental angular frequency. So hence if x of t is periodic and it follows the Dirichlet conditions, that is, it must be convergent and it should have finite number of maximas and minimas, and also it should not have infinite discontinuities in the signal. So in this case, the Fourier series gives us a very simple and synthesizable representation of expressing even complicated signals. So therefore we can say that given that x of t is periodic and it follows the Dirichlet conditions, then any periodic signal can be expressed by means of weighted sum of pure sinusoids. So what does this expression mean? Let us look into some visuals. Now over here we have a signal x of t, which is periodic. So its t naught is until here. So this is our t naught from 0 to t naught, and after that it is repeating. So this is our time period. So say this time period is having a value of 1. Fundamental angular frequency omega naught is simply 2 pi by t naught, and this is, or simply the f naught is 1 by t naught, and that is again 1. So these are the set of informations that we can extract out from this signal. But importantly, this signal is rather involved, and we need to express this by means of some simple signals. And these simple signals should be in the form of sinusoids. That is, they can be cos function or a sine function, and multiples of that. So let us look into how we can achieve that. So again, the red is our target that we want to achieve. So this is our target signal, but we are interested in the synthesis of this signal. That is, we need to express this in terms of simple sinusoids. So this is our fundamental frequency. Or we say this is the first harmonic. That is, we are having this signal over here, which is in terms of a cos function, and this is having a frequency f naught, which is simply 1. Moreover, you can observe that the amplitude, say, is 1, so we have a 1 appearing over here. But we also have this signal over here, which is appearing at this point, and this signal is actually completing 2 cycles in this given time period, that is of 1 second. We say that this signal has the frequency which is twice than that of the fundamental frequency. So this formulates our second harmonic. That is, its frequency is now 2 times f naught, that is 2 hertz. So now we have cos 2 pi and now it is 2. Moreover, the amplitude is now revised. Say this is 1 by 2. So that would be over here. 1 by 2 cos 2 pi 2. Now if we add these two signals together, that is this signal and the second harmonic signal, so we would have this kind of a waveform which is green, that is the second waveform, which is having just one ripple in between rather than having many ripples at the lower end and the upper end. So over here we have a rotating phasor which is just representing one cos function that is expressed over here in this blue signal, which deals with the fundamental frequency or the first harmonic, and we have expressed as 1 cos 2 pi of 1, right? So this is our cos function. Now we also have the second harmonic, which is having an amplitude of 1 by 2. So if this radius was 1, so say this radius is now 1 by 2, right? And this is now oscillating at twice the speed as the first signal. So now we have two maximas and minimas. Similarly, if we add more harmonics, now this becomes the third harmonic, right? So this completes 3 cycles in 1 second for this particular signal. So we have 3 maximas and 3 minimas. Similarly, we can have more harmonics. This is completing 4 cycles in 1 second. So this is actually, this graph is not to the scale, but anyways, it serves the purpose of understanding. So now we have now 4 maximas and 4 minimas, right? So if we keep on adding them, we would start to resemble a square wave or this function. So moving on, so over here we have added more harmonics, and as we add more harmonics would eventually lead to this signal. So as we can say that we have an, which is the amplitude of a given signal, given sinusoidal signal, and this is equivalent to 2 pi nf naught, and n deals with the harmonic. This is our fundamental frequency, and for the first harmonic we have 1, for the second 2, and so on. Similarly, we have a bn sine of the same function. So adding the simple sinusoids leads to this signal. So over here again the amplitudes are expressed in the 3D plot. So this signal deals with the fundamental harmonic, which is having an amplitude, say over here 1. So this is completing 2 cycles in a given time period. So this becomes the second harmonic, and it has an amplitude, say A2, third harmonic with amplitude A3, and so on until the nth harmonic, which is having an amplitude of an. So in short, we have synthesized this into simple sinusoids. So if you add on, you would reach here. Now over here we have the frequency plot. This was in terms of time. This is in terms of frequency. And this is our fundamental harmonic. This is the first harmonic, that is 2f naught. This is 3f naught, and so on. This defines the amplitude of it. So the first having an amplitude of, say, a1. So this is a1 having an amplitude a2, a3, and so on. So the time plot and the frequency plot. So this is simply the magnitude spectrum. Also note that in the square wave, we have a discontinuity at point 0, right? So if there is a discontinuity, then in the Fourier series, we would not be able to track it completely, and we would have some sort of ringing effect at the edges over here. So this is something that we call as Gibbs phenomena. On the other hand, if we have a triangular kind of a shape, so in this case, there is no discontinuity. So we would be able to track it pretty much even with small number of harmonics. So over here, even by 6th and 7th harmonic, we are almost there. But that was not the case for the square wave. So in short, if a signal has discontinuities. So in that case, Fourier series would not be very efficiently following the original signal that we intend. So therefore, we can express the x of t, which is periodic, in terms of weighted sum of pure sinusoids. That is, we can express it as x of t, which is equivalent to a summation k1 to infinity ak, and the sinusoids are cos k omega naught t plus bk sine k omega naught t. Note that we were having f naught or omega naught, 2f naught, and so on. So at this value we have a DC value. This is the DC value or an average value of a signal. So this is simply a naught by 2 and it is added to the series. So these are the weights which simply correspond to the amplitudes, and this k represent the harmonic, that is expressed over here 2, 3 and onwards. For f naught it is simply 1, and cos and sine are the two bases of this series. That is, we can replace the pure sinusoid with bases. So I will come back to the aspect of bases in a while. So since we are synthesizing this x of t into all of these parts, so this expression is termed as synthesis equation. But you must be wondering, how would we find the value of ak, bk and a naught? So a naught is just the average value. For example, in the square wave, the average value of a periodic signal can be computed with the help of just one time period, that is t naught, and you can observe that this part would cancel with this part. So for the square wave, a naught would be equal to 0. So this average value is also called the DC value, and just by inspection you can compute it. Now let us come to the other coefficient, which is ak. So this is simply 2 by t naught and the integration over a time period t naught, the signal x of t, which is expressed over here, times the base with which you are actually comparing it. So now we are comparing ak with respect to this base cos function. So we have cos this k omega naught t dt. And similarly for bk, we are comparing it with sine. So we would have bk, which is equal to 2 by t naught, and again the summation over a time period t naught, the original signal x of t multiplied by sine k omega naught t dt. And to remind you again that ak and bk would formulate eventually the amplitudes, whatever they are. Now all of this is simply the trigonometric Fourier series, which is re-expressed over here. Now let us call this as simply C naught, and this can be simplified into a compact form. That is, we would have a summation again from k1 to infinity ck cos k omega naught t minus theta k, and this is simply achieved from the trigonometric properties. That is, you have an ak perpendicular to bk, so the vector ck would simply be under root ak square plus bk square, and this is our theta k. Furthermore, cos theta k is simply ak by ck, sin theta k is bk by ck, and lastly tan theta k is bk by ak. So now plugging in all these values in this expression, we would arrive at this expression. So as ck is ak square plus bk square under root, and theta k is tan inverse bk by ak coming from here. And this is something that we call as compact trigonometric series. But we know that cos functions and sine function are related with exponential functions minus j theta using Euler's identity. So this brings us to the third kind of Fourier series, which is called the exponential Fourier series. Now this is a very important series because we know that for the LTI system, so if the input is of an exponential form, that is, it is having e raised to power st, so at the output this function would retain itself. So we would have e raised to power st, but this would also be multiplied by an eigenvalue h of s. So hence the function retains itself. Therefore, the exponential Fourier series is of utmost importance among the three Fourier series. And in this formulation, the synthesis of periodic signal x of t is having a very simple form, that is, we have a weighted sum of complex exponentials. The summation is from minus infinity to infinity. And this is since now we have a minus here and a plus here. Again, ak is the weight, and this is complex exponential, and we are having a sum, weighted sum of complex exponentials. Omega naught is the fundamental angular frequency, k is the relevant harmonic. So this was the synthesis expression. Let us derive the analysis expression. That is, what would be ak? So if we multiply both sides of this equation by e minus j n omega naught t, so we would have e minus j n omega naught t x of t, and this would be equivalent to a summation ak e j. Now this exponential multiplied with this exponential would have the following form, that is j k minus n omega naught t. Now let us integrate both sides over a time period. So we have next in the integration on the right side. So this integration would have two solutions. So let us look into both of them. So the first case is when k is equal to n. So that is, we have the integration t naught e, and if k is equal to n, so this will become 0, and then we have dt. So if the time period is, say, from 0 to t naught, so hence the result would be simply t naught. But say k is not equal to n for the second case, so in that case 0 to t naught e j k minus n, this would have some value, and since k is an integer and n is an integer, so this would be having an integer value, omega naught t dt. So this means that exponential is simply cos theta plus j sine theta. For sine, we will be integrating over a time period t naught. But you can observe that this slope would cancel with this slope, and hence for the second case, when k is not equal to 0, this would be equal to 0. So from this intuition, now we plug in the value of k equal to n in this expression. Now we have t naught x of t e minus j. Now k is equal to n, so this would become j k omega naught t dt. And now this summation is yielding these two values of k when k is equal to n and when k is not equal to n. So whenever k is not equal to n, all of this is 0. And when k is equal to n, then this is simply t naught. Whereas for k equal to n, this whole thing would be simply t naught and it would be multiplied by ak. So therefore our analysis expression, that is ak, is simply 1 over t naught x of t e minus j k omega naught t dt. So this is our analysis expression. So hence, as a summary, we have the synthesis equation and the analysis equation over here in the green. Furthermore, again, a naught would define the DC value of signal, a1 would relate to the first harmonic, and an to the nth harmonic. Now you would be wondering, why do we have only three kind of Fourier series? That is trigonometric Fourier series and compact trigonometric Fourier series, exponential Fourier series. In fact, you don't have three Fourier series, but you can have an infinite number of Fourier series. The only thing that you need to consider is that you should have weighted sum of orthogonal bases, that you should have this signal projected or synthesized in terms of bases that are orthogonal. So over here, this cos is orthogonal with this sine function. Moreover, cos 1 omega naught is orthogonal with cos 2 omega naught. Cos 1 omega naught is orthogonal with sine 1 omega naught, and cos 2 omega naught with sine 2 omega naught are orthogonal. Similarly, in the compact form, which is expressed over here, so this cos 1 omega naught is orthogonal with cos 2 omega naught. So the sum are with respect to orthogonal bases. Also in the exponential Fourier series, again that orthogonality is still there, that is ej1 omega naught is orthogonal with ej2 omega naught t. So as long as the bases are orthogonal, we can have a Fourier series. So let us first define what is orthogonality. That is, the signal x of t is orthogonal with y of t if over a time period t naught x of t multiplied by y of t, if these two signals are multiplied and we find the area by means of integration, so the result should be 0. So in the first example, let us take the trigonometric Fourier series in consideration. So simply, if we have cos 2 pi f naught k f naught t, we want to see if it is perpendicular to sine 2 pi k f naught t. So given that we are looking into the first harmonic or the fundamental harmonic, and for simplicity, say f naught is 1. So this signal would simply be a cos function, and from here we have a sine function. So this is our cos 2 pi t, and this is sine 2 pi t. So let us see if they are orthogonal in time period 0 to 1, x of t, y of t. So that is, we have now cos of theta times sine of theta, and this is simply equal to 1 by 2 sine 2 theta. So therefore we would have an integration from 0 to 1 by 2 sine 4 pi t dt, or simply sine 2 pi, and f naught is now 2 t dt. That is, now we have in this period 2 cycles. So this is coming over here. So this slope would cancel with this slope, and similarly this slope would cancel with this slope. If you find the area of this signal, so the area would be 0. Similarly, for the compact trigonometric Fourier series, we can have an example of cos 2 pi t, and we can see if it is perpendicular with cos 4 pi t. So the orthogonality principle says that they are in fact perpendicular. So see if you can achieve this kind of a result for this. Similarly, for the exponential Fourier series, that is ej 2 pi t, whether this is perpendicular with ej 4 pi t. If you multiply these two together, so you would have ej 6 pi t, and we have a time period from 0 to 1 dt. And it is easy to prove that this is simply 0.